Hello my dear students. Shall we summarize what we have studied in the last few classes? Yes, here we go. First we had studied as the postulates of crystal field theory, followed by crystal field theory of octahedral complexes, and that followed by crystal field theory of tetrahedral complexes, and then followed by tetragonal as well as quadplanar complexes. And also we have studied the crystal field stabilization energies related to all these geometry of the complexes, that is tetrahedral, octahedral and tetragonal as well as quadplanar complexes. Now, if we had studied all these, then it becomes mandatory for us to study something about the factors influencing magnitude of crystal field splitting. So, there are actually 4 factors and those influence the magnitude of crystal field splitting. First to say that it is the nature of the ligand, and second one is the oxidation state of the metal ion, and third one is the size of the d orbital, and the fourth one is geometry of the complex. So, let us concentrate on the first topic, that is nature of the ligand and how it affects the magnitude of crystal field splitting. So, it is said that the greater the ease with which the ligand approaches the central metal ion, the greater is the crystal field splitting caused by that ligand, or it is tantamount to say that if the electronic interaction between the ligand and the metal ion is easier, and then there will be higher crystal field splitting. Therefore, we can see that a ligand with higher negative charge and the smaller size and greater sigma donor power as well as greater pi acceptor power will give rise to higher crystal field splitting. So, when we study about this, so we need to concentrate on one more thing, that is said that, or that is spectrochemical series. So, what is this series actually? Spectro and chemical. It is related to the series of ligands in which way it is assigned. So, it is assigned in such a way that all the ligands are arranged in a series where they are arranged according to their strength of crystal field splitting. That is to say that the first ligand will be with the lower crystal field splitting magnitude, and the next ligand will be having higher crystal field splitting magnitude, and it goes on in the increasing order. So, therefore, spectrochemical series is the one which defines the strength of the ligand. So, in general, I can quote few ligands here. So, it starts with iodo ligands or the iodide, and then it will be, or it is the weakest ligand we can call, where it gives the weak field complex, and then next comes the bromide or the Br minus, and it is giving little higher crystal field splitting than that of the first one, that is iodide, and then comes the bromide, then comes the chloride, and then comes the fluoride, and followed by oxalate ions, and then the water, and then by the pyridine, and then by amine, and then by nitrite ions, and it follows the cyanide and also the carbonyl moieties. Now, here water can be taken as the reference ligand, that is to say that below the water what we have is weak field ligands, or above water what we have is the stronger ligand or the strong field ligand. So, therefore, weak field ligands always give rise to weak field complex, and strong field ligands always give rise to strong field complex. Now, here the weak field ligands usually giving rise to a high spin complex. What is this high spin complex? In case of high spin complex, the crystal field splitting is always lesser than, or the crystal field splitting energy is always lesser than the pairing energy. So, therefore, electrons usually jump to higher energy level, and therefore we will get a more number of unpaired electrons, and therefore we see that this complex is high spin. In case of strong field ligands, they give rise to strong field complex, I said, and usually they call as the the low spin complexes. So, in case of low spin complexes, what happens is the crystal field splitting energy is always higher than that of the pairing energy. So, therefore, electrons in the lower orbital cannot jump to the higher orbital. Therefore, they remain paired at the lowest energy state. So, therefore, they give rise to a strong field complex, or they are also called as the low spin complexes, and that is the one thing we need to study along with the nature of the ligand. So, the next factor is the oxidation state of the metal ion or the central metal ion. So, how it affects usually? So in the case of the oxidation state of the metal ion, it is said that higher the oxidation state and smaller the metal ion or smaller the central metal ion, greater will be the crystal field splitting parameter. That is to say that if a metal ion is having higher oxidation state than the lower oxidation state, then it can give rise to higher magnitude of crystal field splitting. So we can make one comparison here in case of cobalt complex. So let us take one example as hexa-aqua complex of the cobalt, where we can have two types of cobalt environment here. One is cobalt with the 3+ state, another one is cobalt with the 2+ oxidation state. So in the case of cobalt 3+, it is noted that the crystal field splitting energy is 18,600 centimeter inverse. But in case of the cobalt 2+ environment, it gets decreased to something around 9,300 centimeter inverse. That is to say that in the former case, cobalt was in +3, but in the later case, the cobalt is in +2. So therefore, this makes a big difference where the higher oxidation state is giving rise to higher crystal field splitting than that of the lower oxidation state. So this is about the oxidation state. Now the third factor is that the size of the d orbitals. Let us see how the size is affecting the crystal field splitting or the magnitude of crystal field splitting. So it becomes mandatory for me to say that if a 3D orbital is there with the metal ion, and next comes the 4D with the metal ion, and if the 5D comes next, then the metal ion with the 5D orbital will give rise to higher crystal field splitting than that of 4D and than that of 3D. Or in general, we can see that the crystal field splitting for 4D orbitals increases by 30 to 50% in comparison with the 3D orbitals, or the crystal field splitting splitting parameter for the 5D orbital that increases by 30 to 50% in comparison with the 4D orbital. So therefore, why this is happening? So it is due to the size. Now let's see how the size is giving all these parameters. So it is said that if the size becomes bigger and bigger, so when the size increases from 3D to 5D, then it becomes easier for the ligand electrons and the metal electrons to interact. That is to say that the d orbital will expand farther into the space, and therefore it can closely interact with the ligand electron. So therefore, if the electronic interaction between the metal and the ligand increases, and it gives rise to higher crystal field splitting parameter. So therefore, 5D is always giving rise to higher crystal field splitting, and 4D is giving next, and then the 3D is the least. So therefore, this is the way of the increasing order for the 3D, 4D and 5D. So we can make a comparison with the 3D6 and 4D6 and 5D6 metal ions. For example, for the 3D6, we can compare it with the hexamine cobalt 3 complex. So in case of hexamine cobalt 3 complex, the crystal field splitting energy comes around 23,000 centimeter inverse. Now, if we move on to the 4D6 metal ion, and that is rhodium, in case of hexamine rhodium 3+ complex, so the crystal field splitting energy is given as 34,000 centimeter inverse. But in the case of 5D, for example, let us take iridium complex. In case of hexamine iridium 3+ complex, the crystal field splitting energy is somewhere around 41,000 centimeter inverse. So increase from 23 to 41,000 centimeter inverse is attributed to the size of the d orbitals, that is increasing from 3D to 4D and 4D to 5D. And therefore we see that as the d orbital size increases, their crystal field splitting energy also increases. Therefore, this is the third factor which influences the crystal field, or which influences the crystal field splitting parameter in case of all the complexes. Now the last one is the geometry of the complex. Let's see how the geometry is giving rise to some changes in crystal field splitting. So we had already studied the crystal field splitting of tetrahedral complexes as well as octahedral complexes. Now we can make a comparison. In case of tetrahedral complexes, what we had studied is the crystal field splitting is always less than that of the octahedral, or we can say that it is half of that of octahedral complexes. Why is it so? So it is because the former one is tetrahedral and the latter one is the octahedral. In case of the former one, what we have is only 4 number of ligands, so that is tetra. But in case of octahedral, and we have the 6 ligands, so number of ligands are increasing, and therefore the increasing number of the ligands also giving rise to higher crystal field splitting parameter or the higher crystal field splitting energy. So therefore the tetrahedral complex is giving rise to lesser crystal field splitting energy than that of octahedral complex. So this is a geometry which is giving some changes in the crystal field splitting parameter. Now, we can also see that because of this lower crystal field splitting, the tetrahedral complex that gives rise to high spin complex. That is to say that in tetrahedral, the crystal field splitting parameter is less, and therefore electrons from the lower energy can straight away jump to higher energy, and therefore it is giving rise to a high spin complex. But in case of octahedral, as we had said, it is the octahedral is giving rise to higher crystal field energy, where crystal field splitting is much more and the gap is very high, and therefore electron from the lower energy or electrons which are located at the lower orbital cannot give rise to or cannot jump to higher energy orbital, and therefore they remain paired at the ground state itself. So therefore we can see that in octahedral, so pairing energy is always lesser than that of the crystal field splitting. So therefore we can conclude that in case of geometry of the complex, the octahedral is giving rise to higher crystal field splitting than that of tetrahedral complexes. And these are the 4 factors which determine or which influence the crystal field splitting energy in the case of all the types of complexes. So with this, in the next class we shall move on to what are the factors actually affecting the stability of the complex metal ions, and then we shall study in the next class. Thank you.